Mark P. Otten back with you.
All right, so this is a big video for you guys. This is your introduction to analysis of variance, also known as ANOVA. This is probably the most popular hypothesis test that psychologists have run across the history of psychology research. Not necessarily one that will continue to be the most popular. I think regression and correlation are probably right behind, and sometimes now psychologists do regressions instead of ANOVAs over the same data and get the same answer, showing that regression actually is a little bit more flexible than ANOVA. But in the end, most psychology researchers know ANOVA and they're familiar with some of the terms and such, and so I need to get you guys to that point. So first term is the moniker, the abbreviation here. A stands for analysis, but then the N stands for the N in analysis, so it's A-analysis. I don't know. It's kind of a strangely created abbreviation here. But this goes back to Ronald Fisher, 1920, something like that. So ANOVA is used to compare two or more samples. So when you have two samples of data, you can actually do a t-test. And we did a t-test for a one sample case, and when you have one sample, the only option really is a t-test. But when you have two samples, you can do a t-test or you can switch to ANOVA, and ANOVA is more popular in this case very often because you can add in a third and a fourth and a fifth sample to compare and still do ANOVA. So a t-test maxes out at two samples, whereas ANOVA can accommodate more data. And so oftentimes in psychology research, you have a lot of data, and so then you start with the ANOVA, and then you maybe pare it down if you're down to two or one, certainly one sample. So the fact that it can accommodate more data is one of the reasons why it has been popular over the years. So when we have three samples, as we're going to have in this example here coming up in the lecture notes, we have a couple of options. We have one 3-sample test and we have three 2-sample tests. Well, there's some decisions here. You could do those 2-sample tests, like suppose you're comparing men and women, men and dogs, and women and dogs, right, on some measure. You could run all three of those tests at the same time, but if you did, statisticians would be like, that's a terrible decision. And so why would they say that? Well, when we run multiple tests, every test that we run is built on this p less than 0.05 rule. And what that means is every conclusion we make is made with 95% confidence. So every time we make a decision, there's a 5% chance that we're going to screw up and make an error. So then, like, the more tests you run, it's like a 5% chance of an error, and then you add another 5% chance of an error, and then you add another 5% chance of an error. And so then, like, if you run a ton of tests, you're increasing your likelihood of screwing up just by probability. And so that's called the probability of type 1 error going up. Type 1 error is making a mistake, rejecting your null hypothesis when you should not. And so what statisticians do is they try to run one big test and then pare it down and follow up with the more specific test, because what that does is it's sort of like a screening process. It's like, okay, we're going to compare all of these samples to each other. Let's say we have 4 samples. We're going to compare them all to each other, and we're going to determine, okay, there is some difference somewhere across these 4 samples. Now we're authorized to go and run multiple tests, even though when we run multiple tests, we increase our chances of making an error. Well, now we've sort of like screened it out, and we're like, yes, there is some difference somewhere. So now, even though we're running a risk of making an error, we know that there is probably a difference, so we're kind of authorized to run those multiple tests. So that's the theory behind it, and that's why we start with one test that compares everything all at once at the beginning, and then usually there's a follow-up afterwards. Okay, I'm going to give you a kind of a silly 3-sample example here to demonstrate ANOVA. So the first group is the contestants on The Voice. Yes, I do watch The Voice. I don't watch too many TV shows, but that is one that I do enjoy. The second group is, this is kind of random, the CSUN men's basketball team, and the third group is the CSUN psychology faculty, pictured there. Okay, so what are we comparing these three groups on? Well, we can make a hypothesis. So there's real research, not on these three groups being compared, but there's real research on, in fitness and health research on fear of gaining weight, or just sort of this feeling of insecurity associated with your weight and how that might manifest in behavior. So we can compare these three groups, and I didn't actually do this, but it's kind of fun to think about. Fear of gaining weight, the independent variable then is group, and so what the dependent variable is going to be is the fear of fat scale. And so what that implies is that your fear of gaining weight, or fear of fat, is dependent on which group you're in. It's dependent on whether you're a contestant on The Voice or whether you're on the basketball team or on the faculty. So you might hypothesize, for example, that the contestants on The Voice are really afraid of gaining weight because they're on TV so much, and like their physical appearance is a factor. Sometimes the men's basketball team maybe a little bit as well, just because they're trying to stay in shape to play. The faculty, I mean, we're kind of like regular people in the sense that we worry about this just as much as you do, but maybe we don't worry about it as much as the other groups, or certainly not the contestants on The Voice. So we could make a hypothesis there such that the dependent variable, again, fear of gaining weight, is dependent on which group you're in. So this is a real scale, the Goldfarb Fear of Fat Scale. I like it partly because it's got a cool name. It's an average of 10 items. Each item ranges from 1 to 4, so this is what they call a Likert scale. A Likert scale is usually like 1 to 7. In this case, it's a little bit shorter, 1 to 4. It's a range. You probably have filled out questionnaires using this kind of scale before to assess the extremes of how you feel about something. So on one end here, it's very untrue, meaning you're not at all afraid of fat, and then on the other end, you're extremely afraid of fat. And so the sample item here is, 1 of the 10 is, I'm afraid to gain even a little weight. So you're going to see some numbers here that reflect that scale, even though this is a made-up study. It's a real scale. So here's what your null and alternative hypotheses look like. You've got a null hypothesis where all three means are equal. Now the key here is to not write the alternative hypothesis with the unequal signs in there. And what I mean by that is, suppose you put an alternative hypothesis mu1 not equal to mu2 not equal to mu3. Well, that would imply that all three means are different from each other. Really, all we need here is one of the means to be different than the other two at minimum. So that null hypothesis remains, but the alternative could be mu1 not equal to mu2, which is equal to mu3, or mu1 not equal to mu3, which is equal to mu2. So there just has to be at least one inequality in there somewhere in the alternative hypothesis. So the simplest thing to do, instead of using those inequality signs, is just to say that the null hypothesis is not true and that there is some difference somewhere between those means. You see your test statistic here. We're using an F test statistic. This is, again, Ronald Fisher was the one that invented ANOVA, and so what did he do? He didn't call it the Fisher method, but he called the test statistic F. And he named that after himself because that was the first letter of his last name. That's why we have an F in our ANOVA notes. So this test statistic I'm going to break down for you. You've got between group variance on the top and within group variance on the bottom. So what does this mean? Well, MS between is the variance between groups. So if you go back to your introduction to variance video, you will see that I introduced the variance as also known as a mean square. It's a mean squared deviation. And what Fisher did was confuse psychology students forever, because instead of calling it a variance, he called it a mean square. And so people are like, oh man, this is a new concept, and oh man, I don't have to learn a whole new thing. Well, it's actually just a variance. So you just have to know what it's the variance of, and then it's the variance of one thing on the top and the variance of the other thing on the bottom of the test statistic fraction, and then you're good. So this is the variance of the group means around the overall or grand mean. And so you're going to have a mean for, and you're going to see this play out in the numbers, you're going to have a mean for the voice contestants, a mean for the psychology faculty, and a mean for the basketball team. That's 3 means, and it's the variance of those 3 numbers around the mean of the 3. So you'll see that in a minute. The mean score within groups is another variance, but it's a different variance. It's the variance of each individual group. So you're taking the variance of the voice contestants, ignoring the other 2 groups, and then the variance of the basketball team, ignoring the other 2 groups, and then the same thing for the faculty. And so if the sample sizes are equal within those 3 groups, then the mean square within is just the average of the 3 group variances. So, and you'll see this play out here in the numbers. So here are the numbers, and you'll hopefully have some clarification as you go along about what these variances really are and what they mean. So we've got our 9 people, hypothetical people. I did not actually survey these people, although I probably could survey 3 faculty right now and get their answers. I could not necessarily do the same for the other 2 groups, certainly not the voice contestants. I don't have them on my texting menu here on my phone at the moment. So anyway, these are made-up scores. The voice contestants scoring high. The maximum here is 40, so they're scoring close to 40. And the other 2 groups are lower. So we can speculate already that maybe the voice contestants have higher scores and are more afraid. All right, so I'm going to go ahead and enter this data into SPSS, and we're going to decide whether the voice contestants really are more afraid of gaining weight than the others. So I've got SPSS open. This is variable view. The key here to data entry is going to be to organize it like it is in the lecture notes slide here. So you're going to just label the first column group and the second column fear of fat, let's say. The group variable then, if you go over to the values column in variable view, you're going to add in some labels here. So 1 is the voice, 2 is the second group, which was the basketball team, and 3 is the faculty. So this will allow you to then have 2 variables labeled like so. The mistake that students make often is to try to make the 3 groups into 3 columns, which is nice for organization, but it doesn't allow you to run the ANOVA in SPSS properly because SPSS will get confused by the format. So there you go for the labels for the group variable. Then if you go back to data view and you enter in 1s and 2s like so, let's say you go 1 or 11, 1, 1, 1, 2, 2, 2, 3, 3, 3, like so, it's going to match your format from the lecture notes here accordingly. So let me show you what that looks like. If you hit the A1 button at the top here, the value labels button, that's going to switch you between the label and the number. And so that will clarify what is what. And so now you can see it kind of looks like the format of the lecture notes here. And again, that's the biggest thing that students forget in entering in the data is to organize it this way, as opposed to, let's say, voice contestants in column 1, basketball team in column 2, and faculty in column 3. That's not going to work for SPSS purposes. So then this will allow you to also just enter in the data down the line here. So I'm going to enter in your 9 values, like so, 15, 22, 23. Okay, so now we're ready to run our ANOVA, and we can go to Analyze, General Linear Model Univariate. Now there's actually 2 different places to go to get an ANOVA in SPSS. There's often 3 different places to go to get the same thing. We saw that with descriptive statistics initially, and getting a scatter plot is in a couple different places, and so on. But anyway, I'm just showing you the one that will get you most directly to where you need to go for your homework. So you're going to go to Analyze, General Linear Model Univariate. General Linear Model means that you have a linear relationship that you're trying to measure between your independent and your dependent variables. Beyond that, I'm not testing you on the meaning of it. It's sort of an overall term that encompasses a lot of our hypothesis tests that we run on that roadmap. So general linear model actually applies to ANOVA. It also applies to regression, and a correlation is also linear. So basically what we're trying to determine is a relationship between IV and DV that is consistent or linear across the different, in this case, the different levels of the IV or the different groups, the voice, basketball team, and the faculty. So in the end, we're just comparing the three means and using variances to determine our hypothesis test. Univariate suggests that there is only one dependent variable. So that's what we've got. So we go to, that was more information than you needed on what that meant. We're going to go to univariate here. We're going to put group over in fixed factor and fear in dependent variable. So group is your independent variable, and in this window, independent variable is labeled as fixed factor. So we can click through, and we're going to get our output here. Everything is piled into this ANOVA summary table. This is the SPSS's version of the ANOVA summary table. It's a little bit more than what is asked for if you're writing up a research paper. I'll show you in the notes what the research paper version looks like. It's a little bit simplified. But you've got your results that you need here. You've got some statistics that lead you to your F value, and then your F value then leads you to your p-value. So I'm just going to talk about the p-value here first. The one that we need to evaluate our null hypothesis, that there is no group differences there are no group differences on fear of fat. It looks like we're going to reject that, right? Because we've got 0.026, that's less than 0.05. So that is a significant effect. That is a rejection of the null hypothesis. And so we can say, yes, there is a significant difference between the three groups here. So we need to follow up with our math to figure out why that happened and where that came from. And so I'm going to save this output. We're going to look at the lecture notes again, and then we're going to come back to the output to clarify where everything falls. Okay, so how did we end up on that p-value? What was some of the math that was behind that decision? I've laid it out for you pretty well, I think, in the lecture notes here. So I'm just going to show it to you and not run through it in Excel, trusting that you guys have some modest Excel skills now to be able to put this in to a spreadsheet and make it work in your homework. So the top part of the fraction is the variance between groups, and so we start with SS. SS is sum of squares, and that's just the squared deviations. It's when you calculate a variance. If you go back to the start of the class, the top part of the fraction of a variance is just a bunch of deviations squared and added up, right? Deviations of scores from the mean, the subtraction squared, and then added up. So that's what we're doing here. Our group means are the three values that we're interested in calculating a variance of. So in this case, we have three categories or three groups: voice contestants, basketball team, and faculty. The three means there are 33.67, 19, and 20. So you can already see that the voice contestants mean is a little bit higher than the other two. And we're going to compare those, and we need to compare them to the mean of those three values, 33.67, 19, and 20. The mean of those three values is 24.22, and that is your what's called the grand mean. Very funny name, I think. The mean that is very grand. So anyway, 24.22 is your central value there to then compare your three means to. So what we're doing is then getting our deviation scores from 24.22. And so, for example, in that voice contestants column, you've got group mean 33.67 minus the grand mean, 24.22 squared. That's a deviation. Then you do that similarly for each of the other two people in that group. Now, the key there is to do it 3 times on repeat and not do a different value for each of the three people in that group. So it's just a repeat. We're not interested in this case in the individual scores, that is, until we get to the other variance that goes in the bottom part of the fraction. So in this case, we're just doing group mean minus grand mean 3 times for each group. For the basketball team, it's 19 minus 24.22 squared 3 times. Group mean minus grand mean for the faculty, 20 minus 24.22 squared 3 times. So those are your squared deviations. Then if you add them up, you're going to get a sum of the 267.59 there is the sum of 33.67 minus 24.22 squared 3 times. Basically add it up 3 times. You can multiply it by 3 or just add it each time down the column. 81.81 is similar, 19 minus 24.22 squared 3 times, and so on. 53.48, 20 minus 24.22 squared 3 times. So those are your, if you add those together, those are your sum of squares between groups numbers. And so at the bottom there you have those 3 sums added up to give you 402.88. So if you get stuck or lost in any of that, feel free to rewind the tape. And if you're still lost, which many of you may be, because this is if you're new to this is a process. Calculating your ANOVA F statistic is a process. So just ask me and the TAs, and we will come around during the computer labs and help you out. You can also visit my office hours and so on. Okay, so the sum of squares between, that goes on the top part of the fraction. The sum of squares within goes on the bottom part of the fraction. Now this it's a variance again. It's a bunch of squared deviations. But this one is as I mentioned before, it's the variance within each of the groups. So you take a variance for the the first voice contestant there. The deviation squared is 35 minus 33.67. The 35 is that person's individual score, and the 33.67 is the group mean. So for that person, you're ignoring the other 2 groups, and you're just doing a deviation of that person's score minus their group mean. The second person, 28, is their individual score. 33.67 is still the group mean. You square that, that's your squared deviation going down, and when you add those 3 together for the voice contestants, you get 52.67. For the basketball team, it's the same. So the X there is the individual score. For the first person, it's 12. The X bar with the group in the subscript, that's 19. That's your group mean for basketball. And so 12 minus 19 squared is your deviation squared for that first person. Hopefully you see the pattern here. When you add those up across each individual person there in the basketball team group, you're going to get 78. And then for the psychology faculty, the first person, 15, subtracting 20, 20 is the group mean, and squaring it, and so on, gives you 38 once you add them up. All right, so once you've added those up at the bottom, everything comes together for 168.67, and that is a measure of the sum of square deviations for within groups. So if this value is high, then that means that there's a lot of variance within each group, or within at least one of the groups there's a lot of variance. So if that's true, that makes it harder to reject your null hypothesis because there's a lot of variance. And so like let's say the group mean for the voice contestants is much higher, which it is. That might lead us to think, oh, we should reject the null hypothesis and say these groups are different. But then there's a ton of variance in there too. So if there's a lot of variance, that kind of takes away from our ability to confidently say that the voice contestant group is higher. Because, well, they're higher, but there's also a ton of variance, so we can't really be sure because everybody's all over the place in their scores, and so on. So that's the logic behind ANOVA. I remember telling my dad when I first started teaching ANOVA about it, and he's a retired clinical psychologist, and he told me, he said, all I remember about ANOVA is that, because he took it in grad school, is something between on the top divided by within on the bottom. I said, that's right. That's what you got here. So the between is the MS, or the variance between groups, and the within is the MS, or the variance within groups. And that's the top and bottom of the fraction. So again, the variance between groups represents how far apart those 3 means are from each other, and that's assessed relative to the variance within each of those groups. And so that's what those terms mean. So in order to turn squared deviations into a variance, turn a sum of squares into a mean square, you got to divide by degrees of freedom. So when this was a variance with the original variance formula, when we first introduced variance, the degrees of freedom was just n minus 1 on the bottom. Now we have 3 groups, and so we got to account for that in our degrees of freedom values. So we have a degrees of freedom between groups, which is number of groups minus 1, as you see there. That goes on the top part of the fraction there, and the degrees of freedom within is the total number of people in all groups minus the number of groups, or the alternative formula for degrees of freedom within is like n minus 1 for the first group plus n minus 1 for the second group plus n minus 1 for the third group if you have 3 groups. So anyway, their formulas are printed there. You don't necessarily have to understand the logic completely on that. You just need to remember the formula is one or the other is fine. We've pulled our sum of squares values from the previous couple of slides, 402.88 and 168.67. And then 3 minus 1 is number of groups minus 1. 9 minus 3 for the degrees of freedom within is total number of people, 9 across all groups, minus number of groups, which is 3. So on that top part of the fraction, then, it's 402.88 divided by 2 gives you 201.44 for your mean square between. 168.67 divided by 6 gives you 28.11 for your mean square within. Divide those two, take a deep breath, and you get your F value, 7.17. Okay, so what does that mean? Well, we're going to go to the critical value table here for F to compare our test statistic to our critical value. We already know that our p-value is less than 0.05 because we found that through SPSS. So we know we're going to reject our null hypothesis if we did the math right here. And we just need to find that 5.14 in the table. All right, so where does that 5.14 come from? Well, first of all, we have degrees of freedom 2, 6. That is your degrees of freedom between, also known as df1, and your degrees of freedom within, also known as df2. So then we go to our table. This is our table that's linked on your Canvas page. df1 goes across the top here. df2 goes along the bottom, or goes along the side here. So our degrees of freedom between is df1. That value is 2, so that's here. That's column 2. Just have to be able to read the table. Everything else is fine. Degrees of freedom within is 6. That's df2, and that's the value of 6. So if we go column 2 and row 6, 2 and 6, the value is 5.14 right there, and that's the one that we used for our critical value to compare for our hypothesis. So it's just a matter of reading the table. Again, if you're going across here along the top, that's your df1, that's your df between value. If you're going down the side here, that's your df2, and that's your degrees of freedom within value. And if you match those up properly, then you've got your, in this case, 5.14 for degrees of freedom 2 and 6. That's your critical value. So then if we make that full screen, then if we have that, we can go back and compare it to our test statistic, and our test statistic was 7.17. So the critical value less than the test statistic, we reject our null hypothesis. And we don't need to worry about absolute value in this case because F values are variances, and variances are always positive. So the 7.17 there is going to be positive. If you get a negative F value, then you know you did something wrong. And so you have to go back and make sure. So this is your world famous ANOVA summary table. World famous because it appears in it's appeared in many a research article over the years in psychology. Like I said at the beginning, ANOVA is very popular, and when you see an ANOVA result, oftentimes you are asked for, or the reviewer of your paper or the person who's viewing your poster or wherever the research is being presented, they often ask for an ANOVA source table to back this up. So what that means, source in this case refers to source of variance. So you've got your between source and your within source. Then your columns are laid out here. Sum of squares, degrees of freedom, mean square, and F. This is nothing new. This is just a summary of the statistics that we already put together. So the only thing that you might see here that's new is the total row there. The total is just sum of squares total. You add that up by adding between to within. So 402.88 in this case, plus 168.67 equals 571.56. The degrees of freedom there, 2 and 6 is 8, and so on and so on. Though that's just for completeness. That's not really for any hypothesis testing purpose. So let me go back and compare this then to the SPSS output, because the SPSS output gives its own version of this. Okay, so this is the SPSS version of the summary table. We've got basically 2 extra rows at the top that are not necessary, and then 1 second from the bottom that's not necessary. So basically, in order to recreate what you've got in your notes there, you take the group row, the error row, and the corrected total row. The error row refers to within, and the group row refers to between. And so then all the numbers should match up. 402.889 is your sum of squares between, 168.67 sum of squares within, and so on, degrees of freedom. Mean square going across there, F 7.166. And then your p-value that corresponds is 0.026. So in order to read this table, it's probably easiest to just get rid of the corrected model and intercept rows, and also get rid of the total row, because the total is not actually the total. The total is the corrected total. That's the total that you want there down at the bottom. You also see r squared at the bottom there, 0.705. So if we go back to our lecture notes. So here in the lecture notes, we see that 0.705 value. Now that is eta squared here, and it was labeled r squared in SPSS. It's the same thing. Conventional wisdoms and conventional ANOVA textbooks call this eta squared. Eta is a Greek letter there. It looks kind of like a N with a little bit of a slant to it and a longer tail on it. That's a Greek letter, eta, and it's squared. And it's basically just sum of squares between, which you already found, 402.88, divided by sum of squares total, which you just found by adding sum of squares between to sum of squares within for your summary table. So it's numbers that you've already got. And 0.705 is an effect size for ANOVA. It is the same kind of interpretation that you might derive from Cohen's d back when you did a t-test, or r squared when you did ANOVA, or I'm sorry, r squared when you did regression. They're all measures in different ways of effect size, and so this one adds to your ability to interpret an ANOVA. You've rejected your null hypothesis in this case, and you've got a 0.705, which is the maximum for eta squared is going to be 1. So the closer to 1 that you get, the greater the effect size is for your effect. So it doesn't have a whole lot of meaning necessarily by itself when you get into comparing your results here to other studies. Let's say you get a 0.705 here, then you rerun the study with more people, or you replace the voice contestants with contestants from some other TV show, you rerun it, you get an effect size there. Then you can, once your effect sizes start piling up across different studies, then you can compare them, and that's when the value of the effect size really starts to take shape. For your homework, you can just do this calculation, report the value, and move forward. Okay, so, oh crap, we should have checked this before. So this is your ANOVA assumptions. I like to cover these at the end, actually, instead of the beginning, because if you cover too many assumptions at the beginning, you kind of, in my experience, you get bogged down with not ever getting to the actual test. It kind of slows you down, makes it like, man, when will we actually get to our results? So what I like to do is do an example first, and then come back at the end and check our assumptions. What the assumptions are is characteristics of your data that need to be in place in order for you to actually run the ANOVA in the first place. So you can't have wildly strange data and run an ANOVA. You have to have certain things in place. And so what those certain things are the following. So some of them are theoretical, others are more like numbers. So the first one is more like theoretical. So we need our data values to be independent of each other within each sample. So for example, in the faculty group, suppose I fill out the scale and then Scott Plunkett fills out the scale. Well, he couldn't have influenced me, or I couldn't have influenced him. If I did, then we would have to delete either my or his data, because they're no longer independent of each other. They're no longer sampled sort of honestly and anonymously. If they're not, then the sample is sort of an experimental design issue. We need to kick Dr. Plunkett out of the study, keep me in there, or vice versa. But given that we are sampling anonymously, given that the people in our sample are not influencing each other's answers, then we're okay, and we can proceed with our analysis. So this was just kind of like implied in our study. It wasn't actually, this isn't a real study that we did, so we don't actually know what happened. But The second one is that the data values within each sample are also roughly normally distributed. So what this means is you can't have too many people piled up at one end of a distribution. Let's say you have this faculty group, right? And you have, suppose you actually sample all the faculty. There's about 30 of us full-time faculty and another 20, I think, part-time faculty right now. So let's say we have all 50 of us. And if everybody was really afraid of fat and scored at the high end, then there would be no normal curve. It would just be everybody scoring really high. And so if you were to graph that, maybe make a histogram and then try to draw a normal curve over those 50 values, you would not get it normally distributed. You would get it sort of clumped at one end. Or let's say everybody answered high and then there were a few people that answered really low. That's also not normal. So you need your data to look roughly normal with a mean in the middle and some values on either side. And roughly, there's no number on that, like how roughly it should be normal. It just is. It's if you have some data that looks strange, then you probably shouldn't be submitting it to an ANOVA. And strange in this case means too much, like skewed to one side or all one number or something like that. Later on, when we get into more, like let's say you take a stats class when you get into grad school, we'll get into that, what that roughly means and how, like the term there, what roughly is really talking about and how to really define something as normal or not in order to be able to confidently run an ANOVA every time. But in this case, you just need to know that it's not super strange data and you're okay. And also, the other thing about this assumption is that if you have sample sizes that are large enough, then you're okay. And this is called the central limit. It's part of the central limit theorem, which you may have heard of in a past math class. So we only had 3 people in each of our samples, so we definitely needed to worry, and if this were a real study, we would have needed to worry about assumption number 2, in that maybe that data was not forming normal curves. But if you get to about 30 or more people, as I said, if we sampled all 50 people that taught classes at CSUN last semester, let's say, in the psychology department, even if it was clumped at one end or something like that, it would actually we would still be able to say something about it because our sample size is big enough, and 30 is the conventional cutoff there. The third assumption here is that variances in each sample are roughly equal. So I mentioned this earlier. If our variances are wildly weird in let's say one of our samples to the basketball team was just all over the place or something like that. Here they did have the biggest variance at 39. But suppose one of them like screwed up and answered like 175 or something really big outlier. Well, that kind of messes you up to be able to conclude anything about the mean of that group, because that outlier is going to affect it a lot, and it's going to, in particular, affect the variance and make it very large. So assumption number 2 kind of goes along with assumption number 3 in that your data needs to not look too weird in order to submit it to a ANOVA. The test here that you can run, this one's more numerical. You can actually run a test here, dividing the biggest group variance among your various groups. Divide the biggest one by the smallest one. And so in this case, we had 3 groups. The biggest variance was 39. That was the basketball team. The smallest was 19. That was the faculty. Divide those 2 values, you get 2.05. And as long as that value is not greater than 10, then you're okay. In this case, it's only 2.05. So we're okay by this criteria to continue with our ANOVA.